Hadera Hashgraph is built on Hashgraph. So what is Hashgraph? Let's talk through this. So Hashgraph is an algorithm, a consensus algorithm. If we can go to the next slide, there we are. It's a distributed consensus algorithm. It is a way for a group of computers to come to an agreement on an ordering of transactions and timestamps on them. The group as a whole puts a timestamp on the transaction, not just one person. It gets consensus on this, and it is secure, fair, and fast. But what do those mean? Well, security. What we want is to be able to know a timestamp on a transaction and where it is in history, and actually know at a moment in time that you know the answer and that you know the answer. And you want to never be wrong. And everyone will know the same answer. That is Byzantine fault tolerance. If you can do that, even when some of the nodes are malicious, and even when a malicious person can even influence the internet and maybe have firewalls and things. That's what Byzantine fault tolerance is. Notice I said you come to a moment when you know for sure. That's different from some of the proof of work systems where you just become more and more sure over time. Those aren't Byzantine fault tolerant because you never know for sure, you just become more confident. And you can start having problems with partitions with that sort of a system. So what you want is Byzantine fault tolerance, where you absolutely know, guaranteed, and as long as not too many people are malicious, they cannot stop this or make you come to a false consensus. So that's BFT. So Hashgraph is BFT. But that's not all. In order to prove that, you have to make some assumptions. What do you have to assume? Do you have to assume something about the timing of the internet? That messages going across the internet will always get there fast and will never be lost, or always get there within some time period. That sounds like a reasonable assumption, unless you've heard of botnets and DDoS attacks. Sometimes the attackers will go out and compromise a number of little computers on the internet, web cameras and printers and little things, and have all of them flood one computer with messages so much that it can't send or receive any messages. It basically shuts it down from the rest of the internet. If you have a synchronous Byzantine fault tolerance system, the one that doesn't have this good property, maybe you could shut down the whole network by just shutting down one computer. So what you want is asynchronous BFT. ABFT is saying that, yes, we can survive that fine. If they shut down one computer, we'll still reach consensus, and we'll still always be right and never be in disagreement. And we'll know that we're right, and we'll know when we've done it. So that's ABFT. We want to be able to survive malicious nodes. We want to be able to survive firewalls that are stopping our packets or letting some through and not others, or delaying them by an amount of time that keeps changing, or all sorts of strange things, and these distributed denial of service attacks, DDoS attacks. So this is what ABFT is. This is the gold standard for 30 years. It's a very old term. There are actually people that have sometimes made up new terms that sound sort of like ABFT, newer terms that are weaker than ABFT. But the gold standard, the one that is stronger, is ABFT. And that's what we've had for decades in distributed computing and in databases and in Byzantine fault-tolerant computing in general. So we have that. But in addition to that, we have something called state proofs that are very important. So the state proof means that you have a client, you have a wallet program on your phone, and you call up some computer in the network and you say, please do a transaction for me. I will digitally sign it to say I want money to move, I want my cryptocurrency, to move from this account to this account, or I want to store a file, or I want to ask you, hey, does this file exist? And the node gives you an answer. It says, no, that file doesn't exist. Are they lying? Do you know they're telling the truth? Do I have to trust one single computer to not be malicious? With a state proof, that one single computer gives you this small little proof. They say, that file doesn't exist in the ledger, and here's a proof that the whole community had a consensus on that fact. They can't lie. That's what a state proof does. Or you say, please do this cryptocurrency transfer from one account to another. They say, yes, it has gone through. Or yes, this is the balance. And then they give you a state proof. And they can't lie. It proves that this was the consensus of the community, and no one bad actor can compromise that. State proofs are very important. It makes them truthful. Furthermore, I said it's the consensus of the community. Which community? What if we forked and there's now 2 communities that I didn't know? No. It not only says it's the consensus of the community, it tells you which community. That's an interesting concept. That is saying that if one of these nodes takes our state is all the files we're storing, all the cryptocurrency balances, all the results of the smart contracts, and it copies it, it forks it, and gets a bunch of other computers to help it, and forms a new network. And so now you have 2 ledgers that have been forked, and each of them starts making changes, and they keep evolving over time differently. This wallet on your phone knows for sure which one it's talking to. It knows that it is talking to the official one that it's always been talking to and its consensus successors, and not to this fake one that was set up or this new one. It knows that it's a separate thing. So of course, technically, you can always copy information, but you can't fool anyone into thinking that it's the original or that it's the official one. So this is what state proofs allow us to do. And this is another form of security that is important. Not the security of the consensus, but the security of the clients that are using the consensus. This is good. Ooh, but you get something else too. It gives you the ability to avoid the forking. Yes, I love that forking thing. It's a great thing. By the way, did you notice that Mance brought up no forking and he meant it in a different sense? He was talking about not forking the code base and the organization and legal controls. I'm talking about not forking the state and having technical controls where, yeah, you could fork, but you could never lie about it. You'd never fool anybody into believing it. So it's 2 different kinds of forking. In other words, what we're bringing is stability. That's what we're talking about. So we have that. And that's what the state proofs give us. But they do also give us something else. They give us the ability to do sharding in a very powerful way. Know what is sharding? Sharding is we have a network of, say, 1 million computers around the world. That's what we want to grow to, is millions of computers, ordinary people running ordinary machines. Anyone can do it anonymously without telling us who they are. Millions of computers around the world. And to really take advantage of this tremendous amount of power, you want to break them up into groups. So we don't take each file you're storing it and store it on every computer in the world. You have a group of a few hundred over here, and you store it in those. And your cryptocurrency is stored in an account, but not every computer in the world has to store it. There's a few hundred over here that store it. Each shard is doing different things. And a transaction has to be approved by the consensus of the shard. And we randomly assign people to shards. Now, if you're going to do sharding like that, there are lots of different ways of doing it. And some people are talking about ways of doing it where everyone is equal, but one shard is more equal. You could talk about we have a real chain and side chains. And this asymmetry can actually cause some problems with the flow patterns of these transactions, where if I have 1 million shards, am I going to be 1 million times faster? Maybe not. It depends on the application, depends on some other issues. What you really want to do is have everybody be basically equal. That Alice has a cryptocurrency account stored in this shard, and it's only in this shard. And Bob has one in this shard, and it's only in this shard. That gives us the better ability of truly scaling up. But then the problem is, how do you make it work right? How do you ensure that the amount of cryptocurrency never changes in the total in the world? That we can send cryptocurrency from Alice to Bob, but Bob just can't create it out of thin air. How do you do that? And the answer is, well, you have the shards talk to each other. They send each other messages. This shard, when it knows that we want to transfer from Alice to Bob, decreases how much Alice has, sends a message to this shard, and this shard increases how much Bob has. But wait, how do you trust the message? If it was just some random computer over here doing it, maybe they're lying. How do we know they're not lying? We use a state proof. So any random computer in this shard makes a message that is the consensus of everyone of this shard. We, as a consensus, agree that Alice has authorized this transaction, and at the point in history where that transaction was, she did have enough cryptocurrency in her account. It should happen. We have reached consensus. This transaction should go through. So they decrease her account, create a message with a state proof that shows the message is valid, And the message now can come over to the shard where Bob is. And the shard says, this was a duly authorized message, consensus of all the hundreds of computers in that shard. We are going to increase Bob's account, and we're sure that we're keeping the rules. Like one of the rules is the total amount of cryptocurrency can't change. We're sure that although we're increasing his account, it must have gone down over there because that was the consensus. And so this is very important for sharding. This allows us then to have a sharded system where there isn't a single master with some sides. Everybody is equal. You may actually have a master shard that assigns people to shards randomly, but that just happens when they join the network. It's not a lot of throughput, not a lot of traffic, and so you can have efficiency. And so we end up having this kind of security. This kind of security then means that if you're using something like Hashgraph inside of each shard, which is ABFT, now the giant ledger as a whole, with all the shards as a whole, is ABFT. We can have security of the whole system because we had security of the pieces, and we had the state proofs that allowed them to talk to each other securely. And that you could use to make things faster. Not always. You know, it's common to say, well, if I had n shards, I'd be n times faster. Yes, sometimes. Sometimes not. Depends on the application. Depends on the pattern of how they interact. If everybody has to talk to one shard, then we all run at the speed of one shard. But if all the transactions are happening between different shards, then we run much faster. So a good ledger ought to have sharding to be fast, but it also had to have single shards that are fast to be fast in the cases where you're limited to the speed of a single shard. We can have both. But that isn't the only kind of security we should care about. A totally different kind of security is bugs in the code, bugs in the theorems. All this stuff, all this math stuff was mathematically proven. But is it true? Math journals sometimes publish proofs that are wrong. We discover it years later. The four-color theorem had false proofs at one point that people believed, I think, for a decade. Amazing. So how do we prove things and trust it? There is something called formal methods, where you turn this proof that humans can understand into a form that computers can understand, and computers check it for you. And people have actually found bugs in widely deployed open source software. When they got down to trying to get the computer to understand the proof, they said, oh, I see, there's bugs in the software. We have a department now, we have a group of people in our team working on formal methods, taking our ABFT proofs, formalizing them, putting them into a computer in a way that the computer can check. And they have already proved some definitions and some lemmas and some parts of it, and they're making rapid progress. And it's on our website. You can get it, and you can look at what they've done so far. It's fascinating. It's really actually very cool. Formal methods is the future of software, I think. And they're doing that, and that's, I said, proving that the proof is right. But you know what the next step is? The next step is showing that your software is correctly implementing the algorithm that your theorem said was ABFT. You just complete the chain. And that's the next step, and we will do that. We are going to follow this chain until we have the whole chain so the consensus software itself is known to be right. And then you expand outwards. Then we do the gossip software. Then we do some of the other software. Then eventually you go down to the operating system and the chip and all those things, and people are working on that. So formal methods are another form of security. Again, it comes down to math, but a different kind of math. COQ is the name of the system we're using to formalize it. Very cool system. Yeah, talk to me sometime about it. It's really interesting. So we have security. But you know what? Security with ABFT is the best security you can achieve. You cannot do better. So we do better. How do we do better? Not by being more secure in the ABFT sense, but by being more secure in a different sense. We have fairness. So let's be very clear on what we talk about, what we mean by fairness. First of all, it's not fairness, it's fairness of ordering, fairness of timestamps, fairness of access. This is what we're talking about, 3 specific kinds of fairness. And what do we mean by that? So here's the idea. You do a transaction, it goes out to everybody, and we really want to know what the timestamp is on it. Maybe we're going to put them in order, and we really want to know what order they're in because we're doing an auction, and it matters what order you're in. So what we should do is we as a community, our consensus algorithm, should put a timestamp on this transaction that is the true time that the transaction reached the community. Wait, the community is not a computer, it's a bunch of computers. At what time did it reach a bunch of computers? That's not one time, it's a bunch of times. I could ask each person in the community, when did you receive it? And I'll get a whole list of times. Oh, well, you know what we can do is we can just say, when did you first reach most of the community? In other words, take that list of times of when each person received it, sort them in order, and take the middle one. That's a reasonable definition of what it means to be the true time at which a transaction reached the community. We don't want to penalize you if there was one straggler that didn't get it for a long time. And we don't want to reward you for just one computer that happened to get it. We'll do it when you reach the majority of the community. And in our gossip protocol, you're going to rapidly reach every single person right after that. So that's a reasonable definition of the right time, the true time. Now, what is that going to be? We take the time when you reach everybody, we put them in a list, sort them in order. What you're going to find is there's a whole bunch of times in the middle that are all about the same, and then there's some outliers, a few that are much later and a few that are much earlier. That's typically what you see, a bell-shaped curve with a bunch of times in the middle that are all about the same. We're taking the middle one. But what if an attacker wants to change this, not change it, but influence it to be not the truth? What if an attacker, one of our nodes is malicious and wants us to have a consensus timestamp that is far from the true timestamp that it ought to be? Well, they really can't. They could say, I received this in the year 37 billion. Okay, so that's one more time at the top of the list. And when I take the middle of the list, maybe I've gone down by half a notch, and all those times in the middle were about the same, so they really haven't had much influence. Or maybe they said, I received it while dinosaurs were roaming the earth. Okay, well, now you've moved me half a slot down this way. But still, there's that big clump of numbers in the middle that are the same, and I picked one. In other words, it is very hard for attackers to drag the time very far from the true time of what it ought to be. And that's what fairness is. If we have 100 computers, each of them has 1% of the vote in some sense. And it's not possible for one malicious computer or a small group of malicious computers to drag you too far from what the truth is. In fact, as long as the majority of those times are honest, the middle one will be honest or will be right between two honest ones. Guaranteed. So this is fairness of timestamps. Sometimes that matters. The timestamp matters. You have a legal contract that says, do this by noon on Tuesday. So now you have a fair timestamp from the community saying, yes, you did it 1 minute before noon on Tuesday. You succeeded. And now, because of the state proofs, you can know for sure that they've agreed. And not just you can prove to a court that you did it before noon on Tuesday. You can prove to somebody else that you did it before noon on Tuesday. We could prove to another shard if we cared about that. All those things. That's the timestamps. More often, more important, is the ordering. Do we have fair ordering? For an auction, you care who bid first if two people bid the same amount. For a game, you care if you shoot me and I dodge. Which one happened first? Did you shoot before I dodged? You get a point. Or did I dodge first? You don't get a point. So often, the ordering matters. But what we're going to do is say that the official order is, well, whatever order the official timestamps are in. Our consensus order is the order of our consensus timestamps. And so if it's hard for an attacker to drag the consensus timestamp too far from what it should be, then it's hard for them to have more influence than they should on the order. So we have fair ordering. We also have fair access, which is just a way of saying these systems are very resilient. What if you call up a node and give it your message? I mean, you're a node. You call another node and try to pass the message on to it, and it's malicious and doesn't pass on your message. Well, who cares? I'm calling 10 nodes a second. Most of them are honest. I will very quickly find a node that's honest and give my message to an honest node, and it'll pass it on. Not a big deal. Or maybe I'm calling multiple nodes at the same time. And if one of them is dishonest and doesn't pass it on, who cares? I was calling other nodes at the same time. Your messages spread out very fast. It becomes very difficult for one malicious node to stop your message from spreading to the community. And if you are a client, you can call up a node and very quickly know whether or not they did it, and they can't lie to you. State proofs again. give you fair access in this sense. They can't pretend that they gave out the message when they didn't. And they can tell you whether consensus was reached or not, and they can't lie. And if they're malicious, they don't do anything, after a few seconds you say, well, forget you, I'll try somebody else. And if you really want to hedge your bets, you can talk to several nodes at once. This is fair access. So fair timestamps and fair orderings is sort of this math proof that it's fair because of various math things, and fair access is just inherent in the nature of this gossip protocol, along with the fact that we have state proofs, which makes things nice, because the node can't lie to you. So this is fairness. Security is great. Fairness is a new kind of security, which is also good. But you know what? Neither of those is of any good to you if you do not have speed. We need the system to be speed. Not every application needs it, but lots of applications need it. And you can get speed by sharding, but if you have certain patterns of transactions, even sharding doesn't help very much. So what you want to do is have sharding, but also have really fast single shards. So the question is, could we handle hundreds of thousands of transactions even in a single shard? And could we reach that latency, the time to finality, of just seconds? Very fast. This is the question. Latency here is the time until you absolutely 100% know you're right. Okay, so let's talk then about the Hadera Hashgraph performance. We have been doing performance testing, and we've been doing performance testing on nodes on Amazon, AWS, spread around the world on 5 continents, and we've been doing it with the number of nodes equaling the number of governing members that we are going to have, and we have done lots of different numbers of nodes as well. We've done lots of stuff. If you want to know all the details, look at our website and get the paper that describes it all. If you want to know about the formal proofs, look at our website and get the paper that describes it all. If you want to know the algorithm, look at the website that has the paper that describes it all. Oh, and you may be curious about our governance. Guess where that is? Hashgraph.com. You look at the website, you find that. So, what does the performance look like? Well, what does it need to be? You know, if you're a major credit card, global, around-the-world credit card, how fast are they? Well, a typical one might run at 2,000 transactions a second on average, with peaks up to over 50,000. So this is the kind of speed we're talking about for a really major international system, is a couple thousand a second, maybe peaking up to over 50,000. And the published requirements from some of these public credit cards are the merchant must, or the system must approve within 7 seconds. You swipe your card in the store and you have to know the answer within 7 seconds. And the answer is usually, please reinsert your card. The chip didn't work. I'm probably the only person that ever has that problem. So what did we do? 50,000. We asked it to do 50,000 on a network spread around the world. Not 50,000 peak, but average, continually doing 50,000 transactions per second, spread around the world into 5 continents, in 8 regions, from Tokyo to Canada, from Australia to Frankfurt, Germany, from Sao Paulo in South America, up to Seoul, South Korea, and both coasts of the United States, which might have been 8. If it wasn't 8, I forgot one. Those 8. And we were getting good speed. If we asked it to do 50,000 per second, we were getting 2.9 seconds of latency. So in a couple of seconds, you have your answer. Not a confirmation, a 100% sure, guaranteed, I know I have the consensus and I know everyone else has the same consensus, guaranteed. That's what we were getting. Thank you. So I'm happy with that. That's good. That means we can handle even the peak of a major credit card system. But just for fun, we asked it to do twice that, 100,000 a second. And of course, there's always these trade-offs. Read the paper. It has all the trade-offs and all the curves and all the numbers. But there's always trade-offs. If you want to do a lot, it starts to slow down your consensus. And it slowed down our consensus by less than half a second. We actually went up to 3.3 seconds with 100,000 transactions per second. This is the kind of speed we're talking about. And this is spread around the world. What if you were willing to settle for a mere continent? What if we were willing to settle for merely across the United States, over 2,000 miles? Converted to kilometers, that's a bunch. Actually, it's 3,000. So over 3,000 kilometers going across the country. And we want to have the same kind of consensus latency that you're seeing here. So just for fun, let me show you that example. What happens when you're in one continent and with the same latency to time to finality to absolutely guaranteeing knowing it? Does it run faster than 50,000? Well, it does run a little bit faster. 250,000. So this, thank you, this is running at 250,000 transactions per second. And look at that latency. It's still just 3 seconds. Now remember, we have all sorts of caveats. This is, anyway, read the paper for all the caveats. I'll say them all again at the end. But these are preliminary results. I think we can make it faster in some ways. In some cases, it'll be slower. And in some other cases, it'll be faster. And in some other cases, it'll be slower. But these are the numbers we're getting. But you know, you just have to try it. That's what a continent looks like. What does one region look like? Like the East Coast of the United States? You just got to try it and see what it says. And what it says, in that case, is 500,000. And it's 3.5 seconds latency. That's kind of cool. So that's just one region, though. We're not going to run a shard in one region because I don't trust it. It's all about trust. But here's the bottom line. It is not that these numbers mean anything. There are lots of trade-offs. If you use more people, it becomes slower. But if we were to tune it, it would become faster. And if you spread it over a bigger region, it becomes slower. But if you spread it over a smaller region, it becomes faster. And there's all of these things. We need to talk about them. They're in the paper, and we will be giving more results in the future. But you know what? If you were just to look at the math, you would think this is an algorithm that really ought to run about the limits of what the laws of mathematics allow and what the internet allows for an ABFT system. Because all we're doing is the bare minimum of spreading out the transactions with their timestamps and signatures to begin with, plus a tiny bit of information, 2 hashes, actually 2 compressed hashes that come down to a couple bytes, just a little tiny bit of extra information. That's the only bandwidth we use. And then the consensus part of it you get for free. That's how the hash graph works. You use no bandwidth at all for the consensus part of it. You just send out the bare minimum of the transactions themselves with their signatures and their timestamps. And then you add a little tiny bit for 2 hashes. That gives you a hash graph. That gives you a history so you know how we talk to each other. And then you get consensus for free. No communication at all. You look at that, mathematically you say, you know, it ought to run about as fast as any ABFT ever system could. And do remember, this is 1 shard. Okay, but, so you know what that means. That means that for many applications, you're going to get n times faster with n shards. For some applications, you'll get 1 time faster with n shards. For most applications, you'll be somewhere in between. So you can be faster in most applications with sharding. But a single shard is this fast. You'd expect it to be about the limits of mathematics, and it kind of looks like that. Who knows? That's what we're seeing right now. It's early days. But what about signatures? We want to have digital signatures on all of our transactions. When Alice wants to move from her wallet or from her account to Bob's account, she has to digitally sign it. Can we verify that many digital signatures? Now, do understand there's digital signatures involved in the consensus itself. We were doing verification. When you see these numbers on the screen, these are for when we had very strong encryption, very strong digital signatures being verified, very strong hashes for the consensus part of this. But for the transaction part of this, for actually verifying signatures on each transaction, how much time is that going to take? And we thought that's going to be very slow on a typical computer. We don't want a supercomputer. We want a typical computer, except maybe we could use the graphics card. We weren't able to find any libraries that would do that, but we were able to get a library written to do that, and we were able to test it, and we were able to see and answer the question, can we verify hundreds of thousands of digital signatures per second if you use the graphics card, one graphics card, on the computer? And when we tested it, what we discovered is that the answer is no. The speed is not hundreds of thousands. It's 1,000,000. Okay. This is what we're talking about. Now, again, if you have a smaller graphics card, it'll be slower. If you had a bigger graphics card, it'll be bigger. But it's a single graphics card. It's very fast. This is faster than we can even do consensus in a single shard. So basically, it looks like it's fast enough. I mean, that's really what the bottom line is. It looks like it's fast enough. All right. Read the paper for caveats. It's early days. I'm sure we'll have various things changing over time, but we would have thought from the math that this stuff ought to be pretty fast, and it looks like it's pretty fast. It looks like it's pretty running at the limit of what you can do. So we are fast, we are fair, and we are secure. Hedera has papers, a white paper you should read. It has other papers you should read. You should look at the really cool math stuff in COQ. That is Hedera. Go to hashgraph.com and download all this stuff and look at it. Download the code and run your own timing tests. It's fun. That is what we are doing. We are Hedera, and you might wonder, great in theory, works on your test net that's spread around the globe right now in 3 continents, but is anybody actually using it? Is there anyone actually using this? Is there a real purpose for what you're doing? Has anybody built on Hashgraph or Hedera? Is anyone currently building on Hashgraph and Hedera? And is anyone about to build on Hashgraph and Hedera? Good question.